Good morning, everyone. Good morning. So it's great to be here. Apart, I think, was a success in so many ways, including, as I mentioned some of you last night, building a community that still is quite durable and persistent. And so it's really a pleasure to be here. This was also a pleasure. This was the view from Vermkogel that Thomas mentioned earlier. You can see the Dolomites if you want. All right, so we're all, as they say, strolling down memory lane this week. So I'm not going to talk about the performance tools aspects of Paradigm. Many of you know that things, some of the automated stuff, resource hierarchies, inclusive, exclusive metrics, a lot of things that we use in our normal terms, derived metrics, things like that, were things that I think we contributed to the field, but I'm not going to talk about that. I'm going to talk about the underlying dynamic instrumentation that was born as dynamic instrumentation, binary code patching. And so I'll talk a little old history, but as Ricky Nelson said, if memories are all I sang, I'd rather drive a truck. I'll talk about binary writing and dynamic instrumentation, the two main flavors of binary instrumentation. I'll talk about our foray into kernel instrumentation, dynamically modifying a production kernel while it's running, what could go wrong. I'll talk about a weird version of it, lightweight instrumentation, that some people say is akin to a virus, called self-propelled instrumentation. And I'll talk about stuff we're doing now, because we're still doing this stuff. So, a little bit of history. Let's start with 1961, the DEC DDT debugger. And DDT stood for the DEC debugging tape. That's the tape. Anybody here had hands on paper tape? A few people. So basically in the DEC PDP-1 computer, their first foray into it, if something went wrong and you wanted to debug the program in memory, you could load up the DDT debugger and then start patching code in memory. And that's actually a descendant of the 1957 FLIT debugger. So that's there. So I wasn't doing dynamic stuff. My notion of code patching started in 1972 when I was in high school. This is an IBM 1130 mini computer. This is the computer. That's actually the card reader. That's the console of the computer. That's the computer I started programming in high school. And my friend and I wrote a basic compiler in assembly language. We ended up selling it to IBM, which I thought was pretty cool as a high school student. And it was like over 5,000 cards long. And boxes in each card, if those of you did punch cards, was 2,000 cards. And a 400 card per minute reader, and with the time to run the assembler and time to load in memory took a half an hour. If you actually made a modification, the time to run your modification took at least a half an hour. And so we left patch areas in our code and scattered throughout there, little BSSs through the code, and then we'd patch in a jump and we'd put the modified instructions and jump back. And that's how so if we found a bug and we wanted to test out the bug, we'd hand assemble it in our head. We knew the assembly language. We knew the machine language in our head, in binary and hex. We could calculate hex differences in our head to calculate branch offsets. These are things you do when you're 16 years old. And we actually patched our code. So allocating patch areas, jumping to the patch area, doing the new code and jumping back. If that sounds like a new idea in Dynast, it actually was one sitting in the back of my head for a long time, but I didn't want to have to do it by hand. So, and the memories actually looked like that on that computer. Right. So, fast forward into the somewhat more into our professional time. Earl Killian built a tool for inserting simple instrumentation to a binary to do kind of basic block counts. That information was fed back into the compiler so the compiler could optimize the code based on what branches were likely to be taken versus which branches weren't likely to be taken. So this Pixie Code Optimizer was an early version, very limited, but this is very limited but automated binary code instrumentation. 1992, a lot of stuff happened. One was at DEC, Srivastava and Wall came up with the OM debugger, which ends up becoming the Atom profiler, the Atom binary rewriter. And Jeff Hollingsworth and I were coming back from Intel after trying to figure out how to get our trace-based tool to run on their new Touchstone Sigma parallel machine, and decided the trace overhead was going to kill us, and decided everything we were doing previously was a failure. Somewhere over North Dakota on a Northwest Airlines flight came up with the idea of maybe you can instrument stuff on the fly and put the instrumentation in and take it out as we needed it and drive it by something semi-intelligent. That was the performance consultant part of Paradigm. And we started building Dynans. So 1992, static binary instrumentation from DEC, taking a binary in, rewriting it with instrumentation, putting out a new binary. Dynamic instrumentation, taking a binary on the fly and modifying it in memory to do new things. Those two somehow took off simultaneously in 1992. We were completely unaware of each other's work, and took a while for a convergence to come. So that was a very exciting period. Okay, binary writing, the part where you take a binary, modify it, and output a new binary. So of course, it has the same benefits that any binary instrumentation has, that you don't need the source code. Sometimes you don't even need the symbol tables. We work on stripped binaries as well. And if you instrument it, you can then share it with somebody else. So if I instrument this binary for whatever, for debugging, for performance, for security, for diagnostics, for whatever it is you want to do, for instruction set emulation, I want to be able to replace instructions that don't run on the CPU, and this my older CPU with a little simulated block of code. All these things people use binary instrumentation for, so I can share that with you. Binary writing is static, so if you want to change the instrumentation in the program, you have to start with a clean binary and re-instrument it again, which can be expensive. Most binary instrumenters only support one or a few platforms, and writing out a new binary is a lot of work because you have to get all the headers, the ELF headers. You have to get, and hopefully you want to get the dwarf debugging information outputted. And outputting ELF correctly is such a fragile thing because nobody's code, nobody's operating system, Linux or whatever, accepts just standard ELF. They have so many other restrictions about things being aligned on cache line boundaries, page boundaries, whatever boundaries, word boundaries, undocumented things that make your binary wrong. So it's a mystery to get this working. And there's no tool out there to take a modified dwarf debug corpus and put it back into a binary. There's tools out there like libdw and libdwarf for reading in and interpreting dwarf, but there's no tool for emitting it. So it's a lot of work to generate a new binary. Even though it sounds simpler to do it statically, it's got some really frustrating hard things. And here's just a bunch of examples, performance, tracing, sandboxing. This is for security, simulating, memory debugging, catching things, code optimizations. Lots of things you can do with binary writing. Dynamic instrumentation, starting a process or grabbing onto a running process and patching it on the fly. When we first came up with it in Dynans, people said, "You're idiots." And we go, okay, that sounds like a challenge. Somebody threw down the gauntlet and we picked it up. Now it's a commodity. There are a lot of tools out there in the world that do that. So again, you don't need the source code. You can change the program as it executes. That was the Dynans thing. Put in some instrumentation at the high level. Some areas you knew weren't going to be productive, pull it out, put more instrumentation into detail. The areas of the code where it wasn't productive, pull it out and drill down more and just do that dynamically on the fly. Jeff Hollingsworth, when he was a grad student, wrote a code coverage tool, which put instrumentation into every basic block that just set a flag when the block was executed. As soon as a block was executed, and the program slowed down. And as soon as a block was executed, he pulled out the instrumentation and the program sped back up. So even though we slowed the program way down, it came right back, and our total performance time was faster than the best commercial static instrumentation tool. So that was kind of fun. So there are times where it's really good. It's more complex because you have to deal with the programs executing. If you patch you got to patch things atomically in memory. If you overwrite a part of an instruction, you might be executing in the middle of it, and you might get a nonsense result. So you have to do some very, very careful kind of playing in memory. If you're doing this on a high-performance computing machine with nodes, you got to have an instrumenter on every node or debugging access on every node. And that's proved challenging over the years. And so, performance, paradigm tracing, all kinds of security things, memory debugging. So the list is pretty similar. Okay. So, binary writing, the static part, it's easier to port, no process control. You get to run the program, instrument the program many times, so you amortize the cost of parsing the binary and instrumenting the binary. And you can often generate more efficient binaries. Dynamic instrumentation, you can insert and move it at runtime. You can execute, you can actually take a running program and say, just execute that function and come back. You can do these really cool things. You can respond to real-time events like forks and execs, so you can actually propagate the instrumentation into new processes on the fly. Dynance did that. And you don't have to deal with ELF and Dwarf or PE and Windows debug files and things like that. So, OM, as I mentioned, was the first general purpose binary writer. This is the Srivastava wall. And it required symbol tables. It could not instrument a program unless the symbol table told it where its functions were. It did some interesting thing. It looked for live variables. It found dead code in the program. It could actually hoist code out of a loop. Compiler optimization, so interesting. Ran on the DEC Alpha, arguably the best processor ever designed, which is why it got killed. We have to live with Intel. And it was the basics for the atom tracing tool. And it worked on .o files, not executable files. There's a lot more information in a .o file than there is in A.out. There's a lot more symbols and locations and things like that that happen to use for linking. This is about object files versus executable files. I won't go through all of that, but it's there sometime if you want to look at it. And OM basically parsed object files into an intermediate form, which is a register transfer language, did the transfer language, and people are doing this now with LLVM's intermediate form. They're hoisting the binary to an intermediate form, they're instrumenting the intermediate form, and re-emitting it. So this architecture that OM came, came up with was actually a predecessor to a lot of modern tools out here. A lot of other binary writers. Jim Larris, Wisconsin, wrote EO for the Spark. At University of Washington, they wrote one for 32-bit x86 and descendant of EEL. So a lot of tools out there, and I won't talk about them all. Microsoft had a short foray into one, which they released for 35 minutes, then pulled it off their website. We grabbed a copy while it was there. Bunch of other tools out there. Okay. Now, there's two kinds of instrumentation that people do, especially dynamically. One is called code patching, the other one's called code caching. And they have some similar characteristics, but they have some differences. So code patching, which is what Dynance did, was don't overwrite code, don't modify code unless you're going to instrument it. So if we want to instrument code, and I'll show you a picture of this so you don't have to follow the words and watch my hands wave. You copy the block that you want to instrument, you transform the copied block to include the new instrumentation, you overwrite the original code with a branch, and then you let the code run, and you branch to it, do the instrumented code, and you branch back. And so you only instrument, touch, or modify the parts of code you want to instrument. So if you want to be selective, this is a great idea. If you want to instrument every instruction, every basic block, this can get a little messy, though there are ways to do it. Now, one of the really important things about this is we can leverage code analysis, parsing the binary and understanding a control flow analysis of the binary. And I'll talk more about that. This is something that we do in Dynans that almost no other tool does. And so we can actually find places in the code and leverage it for this. To do code patching, you almost have to do code analysis. And so I'll talk about it in a little bit. So the basic mechanism is you want to instrument the entry point to function foo. You allocate a block. We call it. We came up with the term trampoline, which is used pretty widely now. You do some pre-instrumentation, what might be saving state. You execute the relocate. So the pre-instrumentation might save state, do some tracing, do some performance counting, do whatever it is you want. Then you have to do the relocated instruction. The one you stepped on with the jump, you have to actually execute it, then you jump back. Okay, and that's in the easy if you say it fast category. There's a lot of fiddly bits, as my British friends like to say. So what happens if you can't fit a jump here because the instruction or basic block is too small to fit a jump? Because in Intel, if you want to do a 32-bit range jump, you need 5 bytes, or else you need 9 bytes of place to do a jump. Or if you patch just before and after. What we end up doing is we relocate the whole function, or we can relocate a whole batch of functions. We allocate some space for the instrumentation, and then we patch a jump in there. So you can relocate individual instructions, you can relocate basic blocks, you can relocate whole functions or whole groups of functions. And you base that on how much you want to instrument at the time, or you base it on constraints about things like that. At the very bottom, most extreme case is if you had a whole list of 1-byte functions. What's a 1-byte function? Just a return instruction, right? If you had a whole list of 1-byte instructions, we'd use a trap instruction for instrumentation. So if you got into the corner weird case where you only could fit 1 byte in, you couldn't relocate things, then you could actually use a trap, which is really expensive, so we didn't like to do it. It almost never happens. So there's a lot of magic here. Okay, code caching. This is the alternative to code patching, is you look at the program as a bunch of basic blocks. You don't know anything else about it, just a bunch of basic blocks. You're looking where the branches are, and when you get to a basic block to execute, before you execute it, you relocate the whole basic block, you fill it up, you open it up with no ops, you write your instrumentation in there, and then you execute this out of the code cache. And then the jump instruction at the end there, let me go back. The jump instruction at the end there will either jump to the next basic block in the cache, or it'll jump to the instrumenter, which will fetch the next basic block in the cache and expand that. It doesn't know anything about the structure of the program except their basic blocks in memory, and that's the whole knowledge. And so every block of code that ever gets executed must be relocated at least once. So even if your instrumentation is only in one place, every block will be relocated. And this is the way the majority of dynamic instrumenters work, because it doesn't require code analysis, so it's a much simpler tool. There's less opportunity to do things smart here, but that's the way most of them work. Okay, so if anybody's seen, that's Jeff Hollingsworth and Bruce Irvin, my first 2 students on that. That's a very young Jeff Hollingsworth. We were all young once. That's actually Paradigm on the screen. If any of you ever remember seeing it, the resource hierarchy, our visualization displays, things like that. So that's actually Paradigm on the screen there. Part of Paradigm was the ability to do dynamic instrumentation. And we weren't smart enough to say, wow, dynamic instrumentation is so cool and it works, everybody's going to want to use it. We were not that smart. Somebody come up to us and go, you're doing dynamic instrumentation performance, can I put tracing in with that? And we go, no, it's kind of built in as an integral part of Paradigm and the daemon, but, and they go, okay. And then somebody else would come along saying, I want to do this debugging thing, can I use your dynamic instrumentation? Go, no, it's kind of integrated into our thing. And then somebody would come along and say, I want to do this other thing. He said, no, after about 5 or 6 times of people hitting us with a baseball bat, we go, maybe Dynance should be separate as a library. Now, separating something that wasn't separate to begin with, as you know from a software engineering point, is a pain in the ass, a royal pain in the ass. And it took us a while to do that, to come up with an abstract, good interface to do that. But we did that, and so we came up with a machine-independent interface for machine-level code patching. And that's something unique about Dynance from other tools. Our interface doesn't know about the instruction set. You can actually drill down to instructions and register names if you want, but you almost never, ever need to talk about the details of your architecture. The instrumenter is platform independent. And so we provide abstractions for instrumentation. We built a binary writing and dynamic instrumentation tool with the same interface. You can take a binary and open it, or you can grab onto a running process, and it's the same instrumentation sequence. It's just a different starting out, whether it's open binary or attached process or create process. And this has been successful enough. If you've ever used System Tap on Red Hat, that's us. Cray has 3 tools now. OmniTrace from AMD is us. HPC Toolkit and Tau have used us for instrumentation. There's a lot of projects I can't talk about that use it. There's a lot of research. Last count, there were like 150 projects out there, commercial tools and research tools that use it. So people like this. Architects are using it for simulations now. Okay. So we had an identical interface for dynamic instrumentation and binary writing. We support code analysis. So there are a lot of code analysis tools out there, and there's a lot of instrumentation tools out there. They're not connected at all. Dynance is unique that we actually integrate the two. You can do instrumentation of the code, which doesn't modify what the program's doing. It just adds information orthogonal. Or you can actually modify the program, change the control flow graph of the program, for example. And you can actually, in the dynamic version, control instrumentation, control the program like a debugger would. Single step it, catch events, start and stop it, read and write memory. And scalability is a big part. The biggest binary we ever instrumented was one from Los Alamos that had 5 gigabytes of Pentium instructions. And we could parse that in less than a minute. Okay, and we actually wrote a paper that went in PLDI, the compiler conference, on how to do parallel parsing, parallel control flow parsing, because nobody had ever worried about that. In the source code world, you just break it down into small source files and run parallel make. You don't have really big files to compile. In the binary world, somebody gives you 5 gigabytes of multi-physics code. Ugh. Okay, so we've always, so there are a lot of binary code analysis tools out there. IDAPro, OllyDebug, Binary Ninja, Anger.io, which is a big project, are out there. Ghidra, anybody heard of Ghidra? 10 years ago, I wasn't even allowed to say that name. It was a top secret classified tool used for reverse engineering by the NSA. I have code in Ghidra that I can talk about now. I couldn't talk about 10 years ago. Ghidra was unclassified 10 years ago. Well, about 80% of it was unclassified. There's still some secret sauce that they kept private. But it's a really great binary analysis tool with a good GUI display, and you can disassemble programs and put symbol names in and do all kinds of smart analysis on the code. No instrumentation in any of these tools. And then there are binary instrumentation tools, PIN, like from Intel, NVBit from NVIDIA, Valgrind, Dynamo Rio, all these tools around. But those are separate. Dynance, I think, is unique that it leverages binary code analysis. So we know in the binary where the functions are, where the loops are. We do natural loop detection. By the way, loops that have multiple entry points, irreducible loops, the algorithms that were published previous to Dynance for parsing irreducible loops were broken. They did not work. When we went to implement in Dynance, they didn't work, and so we had to come up with irreducible loop parsing algorithms that there's a fixed point analysis you have to do in them that they got wrong. So you identify loops, basic blocks, and jumps. We leverage data flow analysis to understand things like pointer values, to try to parse jump tables. And jump tables can be 4 or 5 levels with indexing forward, indexing backwards, sparse crazy structures to do. So we can do that. So we can use control flow analysis to avoid instrumenting unnecessary places. We can use data flow analysis to avoid spilling registers and things like that. So we think this synergy, which is a lot more work, between code analysis and instrumentation was a good thing. So that's where we were. And so machine-independent program representation, when you want to put instrumentation code in the program, you write it in terms of abstract syntax tree objects. Just adds, loads, calls, whatever it is, load, whatever, set up get parameter, get local variable, calculate effective address for this instruction. Those are the kinds of, so if you want to do a memory trace, you do calculate effective address for the instruction, and then you do a call to a trace function. And that's the total instrumentation you have to do to trace the memory addresses your program's generating. Dynance figures out whether it's relative, absolute, base register, whatever it is, and generates the right code for calculating the effective address. So you can write the instrumentation once and run it on many platforms. You can run it on x86, 32, 64, ARM, Power, whatever. And so like if you want to build something that traces the entry and exit of every function, including loading the trace library into your binary and inserting the tracing at every entry and exit point with the call to inserting the call instructions in, is just 75 lines of C++. If you want to trace MPI functions with all their parameters, and we have this nice table of MPI functions and what their parameters are. You can do that in 250 lines of Dynance. So it can be pretty efficient. Okay, so code analysis. I told you basic blocks, functions, variables, call graph. We generate the call graph as much as we can. We do the control flow graph. We can operate on stripped binaries, but if there's symbols, if there's relocation information, if it's a .so and has dynamic linking information, we opportunistically pick all that up to parse the binary. Because if you're parsing a binary and some function's only called from a virtual function table or a function pointer, you might not find that function in the binary. It'll just be a hole. And is that hole in the binary data? Is that hole in the binary a page alignment gap? Is that hole in the binary dynamic linking tables? You don't know what that hole in the binary is. And so you can't just parse these holes unless you know what's there, though we use some machine learning to look at those holes to try to tell what they are. So every bit of symbol table information we can harness can make our parsing more efficient. We can do runtime code generation, and we base our instrumentation on transformations of the control flow graph. So any Dynance modification of the program you make is based on a valid modification of the control flow graph. We defined an algebra over a control flow graph that's closed under valid control flow graphs. So if you want to rearrange the program, move branches around, move the call stuff around, you can only do so in a way that will result in a valid program coming out. You can't ever get a jump into outer space or falling off the end of the earth. So that's kind of cool. Drew Burnett, when he was doing his PhD, came up with some brilliant formalisms there that are actually very practical. And we can attach to running processes, we can monitor their status change, get callbacks when they do things like fork call exec or signal, and we can do, okay. So yeah, this is our code instrumentation. You write these AST little things about what you want the instrumentation does, and it gets generated into something. We don't do Spark or MIPS anymore, so I pulled this slide out of the archives. Oh, by the way, just as an homage to the old days, I'm using a dark blue background, which is what I used to do back in the apart days. I used to use a dark background in the old days. Now I used to go back to a white background. So this blue background is a subtle homage to the period. Also, I had a bunch of slides already with blue backgrounds, and I didn't want to redo them, so I made the whole talk blue background. Okay, code analysis. Parsing a binary is easy to get the first 80% of it to work. And then you spend the rest of your life trying to get the next 20% to work. Brian's sitting there with a slight smile on his face because he suffered some of the slings and arrows of binary instrumentation. And anybody ever worked on the project varied between two mindsets. One is, I can't believe we can do this. And the other mindset is, I can't believe what a complete piece of shit my binary parser is. Because you have these moments where you think you're doing magic, and you have these moments where you're not doing something right, and you don't know how you'll ever fix it. Is that fair, Brian? Okay, so control flow analysis, function entry points in stripped binaries I talked about, trying to find them when a function's only reachable by a pointer. We have various machine learning magic. Wow, machine learning, who'd have think? Non-standard ABIs, if a function's only called within a single module, you don't have to use the standard C, C++ ABI. You can put values and registers anywhere you want because the compiler's generating the caller and the callee. You can leave stuff in a random register and the other guy can just pick it up if the function's not called from anywhere else. So you have to deal with non-standard ABIs. We identify loop entry and exit. Let's say you want to instrument a branch not taken. A conditional branch, and you want to instrument only the branch not taken edge of the control flow graph. There's no instruction in the binary that you can instrument uniquely for that. The branch not taken edge could be the fall through, but somebody else could get there from a jump. So you can't just instrument the instruction afterwards as the branch not taken, because then you'll instrument potentially something else. And the same if you want to take the branch taken edge, you can't just instrument the destination because somebody else might get there from a different place. So you actually have to copy the code, clone it, modify it, and put instrumentation into this copied transform code. But a programmer loves the idea of saying, I want to instrument the branch not taken. It's so attractive. But with tools that do that code caching, that don't do the binary analysis, the code analysis, they don't have the ability. They have to write all that themselves by hand. So it's hard to explain to people why you want to do this high-level abstract interface until you start writing instrumenters with it. And then you appreciate how much work you save. Okay. We do data flow analysis, which is in compiling, slicing, symbolic information evaluation. Liveness, which is which registers are in use. So if you want to instrument something, I can instrument without spilling a register if I know there's a register free. And we harness that all the time. And so, okay. And we're constantly at battles with the compiler. We instrument code, the compiler generates something that's completely, if you'll pardon me, batshit crazy. And then we have to, and it breaks our analysis. Some assumptions that we didn't know we made. And then we have to increase the smartness of our analysis. So it's a challenge. Oh, so this is just a quick look at what Drew Burnett did on control flow graph editing. If you want to modify the program, like if you want to split a basic block, if you want to join two basic blocks together, if you want to clone a basic block because you only want to instrument one instance of it, not another instance. If two people are jumping in the same place and you only want to instrument one use of it, you can clone it and make two different copies of it. There's all sorts of things. So there's a whole section of Drew's chapter of these cute little cartoons, which was really fun defining a formal algebra with pictures. We decided that was really cool. Our compiler people love this. So you don't see any of this. You never do this. You just do modifications to the program, and underneath it's using this algebra. So, okay. Here's an interesting example. you want to instrument the entry and exit point of every function. And it's important you don't miss any entry points or exit points. But the compiler did something called tail call optimization. How many people are familiar with tail call optimization? Anybody? Okay. Brian's going, this is like PTSD for Brian. He's recovered from all of this, and I'm sorry for the pain again. So A calls B, B calls C, and C is the last thing. The call to C is the last thing before the return. Then he calls C, and the compiler is smart enough to return all the way back to A. Instead of return. It just pops the whole stack off. Now, that's really good for the compiler's point of view, but if you want to instrument the entry and exit, we miss the exit of B. So now your instrumentation's all foobar. Okay, so we actually took B, and this is what it looked like, the save restore, and I think this is Spark code because I have the slide for it. I didn't want to rewrite it in x86. But now we rewrote B. We de-optimized the code. We took this beautifully optimized code the compiler wrote and we de-optimized it. And then we instrumented the de-optimized version so it would behave the way the programmer would expect. Okay. This is the kind of stuff you have to do when you're doing binary instrumentation, and you want the binary and the source code have a very casual relationship. There are things in the binary that are very difficult to map back. You can map the source code down to the binary, but mapping the binary uniquely back up to the source code is really hard. There are many interpretations of that. Is this an outline function, or is this just an internal, just a basic block in the function that's in a different part of the address space? How to map stack up is black magic. Okay, let's see, where am I for timing? I don't want to talk. Okay, I'm not going to talk about res overhead. Read this, as my legal friends would say, read this as read. Kernanst. What a great idea. I want to grab onto a running production kernel, parse it on the fly, and insert, remove instrumentation. Remember when I told people, said we were idiots about dynast? When I suggested this to people, they said, you people are flipping idiots. So, but we did it. This is Ari Chamches's dissertation. It looks almost like dynast, except it worked on the kernel. Inserts code into the kernel on the fly. Everything works, no recompile, boot, or pause. You can't pause the kernel when you're running. I mean, now you can do it if you're in a virtual machine. In the old days, when there are no virtual machines, pausing the kernel was called a crash. So we didn't do that. And it ran on several platforms. Basically, there's a kernan's daemon, which would parse the kernel. We had an agent we inserted into the kernel, which is called dev kernan's, which would help unprotect certain areas of the kernel, because the kernel writers said, nobody should ever modify this part of the kernel, so we're going to make it write protected. But they weren't expecting us to come along and modify the kernel on the fly. So we had some stuff in here. We allocate a patch area for code we inserted that was shared between the daemon and the kernel, in a data heap for instrumentation, and then we wrote a okay. So that worked, and there's a lot of papers on that. So we let that code base rot. So we don't currently have the kernel's code base. Well, I wish I did. I just don't have time for it. But the idea was evolving kernels that you could run on a commodity kernel, and you could measure its performance and dynamically optimize the code as the kernel is running. So the idea is that you measure the behavior of the code in the kernel, you discover something about it, like there's a specialized version of the kernel malloc that's commonly called on 1K or 4K blocks, and I can substitute in a kind of malloc. or there's code that has bad iCache performance because the blocks are in the wrong place. So I can relocate the kernel's basic blocks on the fly in a new version of the code, and the kernel will get faster and faster as longer it runs. So I can also install debugging, and I can install code patches into the kernel on the fly. So we did that. And we did several of these, but let me tell you about one of them. This one's called outlining. If you write code, you have a lot of if error condition, then do this, else do the normal case. If error condition, do this, else do the error case. So interleaved between all your frequently executed code is all your executed code, all your error code. Your normal code, error code, normal code, error code, normal code, error code. So your frequently executed code is interfered with by all the error code that's not frequently executed. So the iCache is full of stuff that doesn't get executed. So you have really bad iCache form. We didn't observe this, Pettis and Hansen did, and they wrote a static tool that would take a binary and watch it execute, and then re-output a new binary with the basic blocks moved around. You change that jump equal to jump not equal, and you move the block out of line. You just change the polarity of the jump instructions and moved all the frequently executed blocks together. So we decided to do that in the kernel. So we first would insert counter sampling code in the kernel in some part to measure iCache miss cycles using hardware performance counters. If any part of the kernel showed up as a lot of iCache miss cycles, we would then measure basic block counts on every basic block in that part of the call graph of the kernel and say which blocks are hot, which blocks are cold. And then we'd rearrange the basic blocks by changing the jumps and moving the cold blocks to the end and packing the hot blocks together. So this is something we really measured. This is part of the underlying file system code. This is file create, and several functions. So you have hot blocks, cold blocks, hot blocks, cold blocks. It's actually more noisy than this, but it kind of looks like this. And we'd measure it, find out it had bad iCache performance by using hardware counters. We'd put counters into every basic block, and then we'd see which are hot and cold. The counters are either really high or really low. It's not ambiguous at all. And then we'd allocate a new version of this code copied over, doing approximately this. And then replacing that code, the old code, with a new one. Where all the hot blocks are together, all the cold blocks are out there and not in the cache. So this worked all on the fly. Just push a button and this worked. And so we did this. I have some numbers for the TCP output routines. So we tested their TCP on this host, and we ended up speeding up TCP performance by 7%. Just by rearranging the basic blocks. And this is just a study of what we did. There was 4K hot blocks, 14K cold blocks. And we talked about, this is just a reduction. We could reduce each execution of each function. If we reduce iCache stall cycles by this much, we could reduce branch mispredict cycles, and we can increase instruction per cycle by that much. But basically, this is a picture of what the iCache looked like for the TCP part of the kernel under our study. And pink or orange meant that those blocks were under there were at least 3 different places, 3 different things fighting over the same location in the iCache. Or 4 things fighting over, and a bunch of places where 2 things are fighting over it. So every place where those numbers are above 1, you're getting iCache miss hits. When we rearranged the hot and cold blocks and ran this again, we got this. So the only iCaches we missed were the original fetches into the iCache in that part of the kernel. So that was really cool. So the idea you can modify the kernel on the fly while it was running, and the kernel's just getting faster and faster. This was really, really fun. So one of my students drew this picture. It's kind of like working on the engine of your car while you're driving down the highway. But I like to point out this is not as dangerous as it looks, because he has the seatbelts wrapped around his feet. So it's all okay. Okay. I have this whole lightweight instrumentation thing to talk about, which I'm not going to get to. Really fun slides. I'll give that at the 50th anniversary talk. So let me talk about some other things that we've done and that we're doing. We observed back when Tia Newhall was doing her dissertation, which was many years ago, she's long been a full professor now, so that tells you how long ago, that languages at the time like Java were interpreted, and measuring the performance of an interpreted language doesn't work by measuring the performance of the interpreter. So measuring the performance of the interpreter at the binary level, so we had to figure out how to instrument the interpreter and how to instrument the interpreter to profile the interpreted instructions, and so we could look at the application performance and also profile the interpreter at the binary level to look at the behavior of the interpreter itself and look at the interaction of those two effects. And I've actually had a discussion just last week of reviving that, because we know we have Python and Perl and Ruby and JavaScript and all these languages, and so this is an idea that was really good, but we really need to bring back at some point. Lazy evaluations, parsing 5 gigabytes of binary, you can't do it efficiently by parsing every byte and doing every analysis on every byte. So you have to be able to parse things and you forget them and reparse them later, or skip certain parsing and only on-demand parsing. And there's a lot of work, and we've done that over the years, and we've gotten it right and gotten it wrong, but this is really important for scale. And I talked about parallel parsing. We started a few years ago. We worked pretty closely with John Melacrumy's group, and John was on sabbatical and he wanted to hack on some code, so he worked with my PhD student Xiaozhu Meng on parallel parsing, and that's trying to do that control flow analysis in parallel. And there are two things that are hard about it. One is our code base was not designed for it. And that whole re-engineering of a code base to do something that was never intended is just hard. And the other thing is parallel parsing for control flow analysis is hard because you want to lock an edge in the control flow graph. But if you lock both ends of it, you prevent, like if it's a call function, you prevent parsing the callee while you're parsing the caller. You get a lot of places where you create serialization that you don't really want. And so we had to invent a whole lot of new data structures that the compiler community never ever invented. And so this was really fun. And we can speed up on a multi-core, on a 32 core chip, we can get up to 20x speed up on our parse time. It's really, it really makes a huge difference. And so we're in the middle of doing GPU analysis instrumentation. Vector, SIMD, SIMT, all these instructions require new techniques because in the SIMT world, SIMD world, you often have mask registers that says these cores will do the instruction and these cores won't. So an if-then-else is every processor executes the then and else instructions, except on the then side, the mask says only these cores actually do the instruction, and on the else side, the converse of the mask, the other instructions do it. So there's control flow analysis that you need to represent things in the control flow analysis that aren't in vector instructions, that aren't there in serial instructions, in scalar instructions. So control flow analysis is really hard. Data flow analysis, we now, if you're doing a parallel vector thing, every core is doing its own part of the vector. So the data flow analysis for that is easy. It just looks like scalar data flow analysis. It's just same kind of calculation, just everybody's in their lane. But some data flow instruction, some vector instructions cross lanes, permute or move stuff around or reduce across the whole vector. So doing an efficient data flow analysis that can represent efficiently when everybody's in their lane, but represent expansively when you're going across lanes is very complicated. And there's nothing like that out in the literature. And that's actually something we're working on right now. And then how to instrument vector instructions to efficiently execute instrument vector code. You're doing vector or SIMT code, you want to use the vector instructions to efficiently do the instrumentation. And so these are all things that I don't know how to do yet. And we're working on right now. This is really fun because our compiler people are going, what? No, we know how to do that. No, we don't. Wait. So, and we have some really good, we did some work in the security world in binary forensics, which was looking at some binary code and saying, now simple things like, what language was this piece of code written? I look at a binary and say, is this Fortran or C or C++? Which compiler compiled it? Which compiler version, which optimization level? We call that toolchain provenance. It's actually really interesting, both in software maintenance to figure out where the code came from in your binary, and also in the security world for doing reverse engineering and analysis. People want to know that kind of stuff. But then we said, we had this idea of saying, can I tell your programming style from the binary? So you know, if you worked on a project, you can tell each other's programming style quite often. You look at the code, you go, oh, I know Tomas wrote that, Mikhail wrote that. You know, I can tell who wrote that code. And our theory was, even after compiling, even after stripping, even after massive optimization, where your code is spread all over, that your authorship signal was still there. We proved, yes, it was. We actually won a couple of AI conference awards for this work. And now there's a whole field on that. So we could actually show authorship style. So we're looking at malware, and because malware is written by teams, the bad guys use really good software engineering techniques. And whether it's a Chinese military gang that's not military because they're in a building just outside the army base, or whether it's a Russian mafia or intelligence agency, wherever it is, you can look at different blocks of code and say, are the same blocks of code in these different pieces of malware, is the authorship appearing in more than one place? Can we build graphs of social networks of bad actors out there? And this is something that we actually showed you could do. And it's being applied in places I can't talk about. It's doing actually some good stuff out there, I think. But you could also do things saying, does that software product by this big company have some of my code in it? They won't give me their source code to tell, but I can look at the binary and find my authorship style in the code. And that's good enough to get a court to order them to give me their source code. So for intellectual property rights, we actually worked with a law firm on a case doing this. It was really cool. The judge was, I don't understand this, but give them your source code because it seems like you should. And so it was fun. They won the case. Okay, Al Spector used to be a VP at IBM, famous researcher from CMU as well, said at SOSP, the most successful technologies have low usage complexity in spite of substantial internal complexity. The old phone system with a dial was a phenomenally complex global network, digital network, but it was this little dial or 10 and 12 buttons. Okay, so we like to think Dynasts, I don't know, maybe that's a little arrogant, I know. We're much more complex to use than a telephone. Well, not one of these phones. These are really a pain, but binary code is so much more complex than it was 30 years ago. It is so much harder. So many assumptions we used to make are dead. And it's so much harder. So we have to keep up with what's in the compiler technology to do that. We had a discussion about dynamic adaptivity. Dynamically adaptive tools are needed to deal with dynamically adaptive systems. That's just something true. Everything's changing. Instruction sets are changing. Architectures, accelerator architectures are changing and being created so fast we don't know how to keep up with them. OS interfaces are changing. Standards like ELF and Dwarf are changing. Everything's changing. It's making our life insane. And then not just accelerated, but TPUs. Have you ever looked at the market space for machine learning accelerators? There are some real data flow machines are back. Those of you that used to love the transputer, you'd love some of these new products that are coming down the line. They've rediscovered the transputer. So this is all. So I'm going to retire before we solve all this. So hopefully the next generation. Okay, thank you all for your time.
Excellent, wonderful, inspiring early morning. Compilers. Fully agree with what you were saying about compilers are like black boxes which are double or triple locked for us, usually. Almost no publications about the exact implementation, the optimization, the algorithms. But in some cases, we can talk to those. They are humans, aren't they? So I remember in some cases being able to talk to them. In some other cases, they saying, just go away, this is,
Yeah.
So can you have further insights about this?
We've done this over the years a lot.
Yeah.
Like when we're doing that provenance, that toolchain provenance stuff, we could tell you which compilers were massively changing their code generation from version to version, GCC, no self-control in that compiler group. Really interesting. So something finishing a paper now. We were told on GPUs, and we're working with AMD on this one, that there are machine learning kernels on the GPUs that are so optimized, there are no free registers anywhere in that code. They use the maximum. So if you want to instrument, it's going to be very expensive to find a place to spill registers because you don't have stacks to spill onto in the GPU world. And they said, you're just screwed, give it up. So we did a study. We have Dynast partially working with the AMD GPU. We can do complete code analysis. So we did a liveness analysis for MIOpen, which is the machine learning. It's like 700 kernels for machine learning. That are supposed to be the difficult. Everybody points to it and said, you're screwed, look at MIOpen. You're screwed, look at MIOpen. So we looked at MIOpen, and we discovered less than 1% of the instructions in every kernel use every register. And in fact, we almost always have at least 3 registers available, which gives us a pointer to the memory, the patch area for the data instrumentation, and gives us a register to hold our virtual thread ID so we can look up the right area and just whatever. We had plenty of registers. But the compiler people said, you're dead. The applications people said, you're dead. We looked at the binary and go, huh? So this is a case, and now we're giving the information back to the compiler people and said, here's a tool that you can measure your efficiency in packing the registers. So the compiler people in a modern compiler world have no idea what their code looks like. But we found that if you can give them a tool and evidence, they will listen to you. And this is as true. So this is going on right now. So this has been happening the whole history.
Bart, you mentioned increasing code complexity, binary standards. So if you think about it asymptotically, if the complexity continuously increases, it will at some point probably exceed the manpower available to your projects. And So
Yeah, I'm hoping to retire before then.
yeah, in the area, so we're talking about compilers. In the area of compiler, there's now this LLVM effort. It does not really directly, it does not allow you to directly modify the binary, but at least the LLVM intermediate representation. Is that something that you thought about taking advantage of? So moving your abstraction level maybe a tiny bit higher to intermediate representation
It's
in exchange for saving some or reducing the complexity, or at least sharing some of the work that deals with that complexity.
There are tools out there that hoist the binary to LLVM intermediate form. And then they work on it, then they use the Clang LLVM infrastructure to regenerate the binary code. And that is a valid approach. And we've talked about building an LLVM emitter for Dynast. And then, because our code analysis is better than just about everybody else's. And so, and I'm sorry, that sounds a little arrogant, but we've done measurements of it. So, and so we've actually talked about it, but we haven't done that. I don't, at some point, you know, we might do that. But there are tools that are just based on that, basically hoisting up to LLVM intermediate form, and then modifying the LLVM intermediate form, because there's a lot of LLVM tools, and then re-emitting it. But we like to keep the artifact completely the same and only modify the sections you want. And where if you do the LLVM, you get quite a different artifact. And so there's different uses for different approaches. But that's definitely a valid approach.
Yeah, thank you.
So I think most of our tools use the source code instrumentation.
Right. Do that when you can, because this is a pain.
I know it's a pain, yeah. But you have the advantage that you are working, you can use the abstractions that you have in the source code, right? So MP abstractions, MPI abstractions, and so on. So, and I think that was always one of the reasons not to use binary instrumentation for us, right? So is this still true, or is it are there advances to actually map back, and what can be mapped back, and what you can't do?
Well, I have a colleague in our computer engineering department who's looking at machine learning kernels and trying to derive out of this kernel the high-level algorithm. Like, oh, this is a matrix multiply, oh, this is some kind of vector thing, this is a tensor operation. So he's actually using machine learning to extract high-level constructs out of the binary code and map them upwards. And it's, in some ways, I mean, it's tricky. Anything with binary code and machine learning is hard because the feature space, if it's images or words and things like that, there's a bazillion papers about feature spaces. Binary code, feature spaces, not so much. So he's able to actually pretty successfully pull high-level constructs out of the binary code and label them. And so that might be in the direction you're talking about. And so I think that's a place where machine learning would be a lever.
But what about HPC toolkit, for example? So they are using binary instrumentation,
right?
So they can keep the connection to the OpenMP level, right? So
well, yeah, because we can instrument what an OpenMP, we instrument OpenMP also, and we know what OpenMP functions do and things like that. So because we can instrument the entry point to any OpenMP function, we can instrument the internals of OpenMP if we want to find out where there's common operations.
But the source code, if you have a parallel loop, you transform it into a function which is then called from the threads, right?
Yeah. Can
you map it back to the original parallel loop in the application then? Or is this connection lost? I mean,
there are calls that set up the parallel loop.
Okay.
And so you can detect those calls that set up this threading structure in the parallel loop and use those, and those you can map back to the parallel structures. So there are enough clues in there for things like OpenMP to pull that all the way back to do that. Yeah.
So I followed the compiler research system quite closely, much more closely than performance tools. And if you really look at the state-of-the-art research the compiler people did, I really have a hard time how you could trace it back from the binary to the sources. So for instance, they aggressively move send receives around. Right? So there's a loop in each side, there's a send receive, and then move it out like several loops the opposite direction. Then how you can keep track that this send is actually coming from that loop. Or a lot of these compilers also generate additional code, additional loops for the runtime.
Sure.
To do the scheduling, which you see in the binary,
Yeah.
but if you bring it back to the user, he has no clue from where this loop is coming from, it will generate it from it.
Exactly. And there are functions that disappear. They get inline. And there's functions that get created, that, thunks, accidental entries. And so we're limited in the ability, if you hoist something out of a loop, classic optimization, I can't tell you that was original, from the binary, I can't tell you that was originally in the loop. So if there's dwarf, I can attribute it. But if there's no dwarf, no debugging code, I can't attribute it. I can tell you what that binary is doing, and I can tell you by function in which basic block it is, but I can't tell you that the compiler made it better or worse.
And the most widely used open source compiler is NVM. This one in particular bad. You transform or you input to the internal representation is really so complicated.
I have an undergraduate looking at a project where they're taking the binary code from no optimizations, which don't ever do minus O0. Don't ever use minus O0. It generates code that's weird and potentially wrong. Use OG, little g, for like debug. Don't ever use O0. It's just, in the Clang or GCC world, it generates bizarre code in the modern day. Use OG. But look, he's looking at OG versus O3. And actually trying to do control flow graph differences between those two, and then basic block differences between the two. And that's so you might be able to do, by doing differences between the optimizer on, the optimizer off. And you can't ever turn the optimizer fully off, because the optimizer gets integrated into the lower levels of the code. So it's just whether I'm doing kind of mild optimization or insane optimization or somewhere in between. So
they used to be called translators in the early days.
Yeah.
And then when future compiler people started introducing, including optimization, they changed the name to compilers.
Yeah, right.
Now the translation is actually a few percent of the compiler.
Sure. And
is optimizing.
And the data flow analysis associated with that optimization can often be the most expensive thing in the code. So there are some techniques you could do for trying to answer that question. Most of the people we talk to don't need to know exactly per line in the code. But if you didn't want to know per line in the code and you had debug information, we can attribute it. And John's, because we work so closely with HPC Toolkit, they actually use the dwarf information to do the careful attribution. Well, thank you all for delaying your skiing to listen to this.